Hi class, welcome back. We're starting our first online lecture series with periodization. If you remember when we went over the syllabus on the first day of class, I said that periodization was the second most important lecture behind program design. So throughout this lecture, we have about 50 slides to cover in multiple different videos. We'll learn the importance of periodization and how it is used. So what we're going to learn how to do is apply the program design variables to various phases of a training program. So throughout a sports season or over a specific time period. What periodization is its fluctuations in volume, intensity, and technique training throughout those seasons to hit a peak in competition or peak in performance. But we first must understand how the body responds to a training stimuli, what kind of effect that training stimuli can produce, and how the body learns to adapt to different training stimuli over time. So here are our objectives, and this is kind of the first part of the video. We're going to learn some different training effects that take place on the body. That'll be the first slide we cover. And then we'll get into some different theories, syndromes, and what these theories do is they're going to help us understand how the body responds to a stimulus. And then we're going to understand how does adaptation occur due to various training stimuli. So we first must understand how the body adapts to a training stimuli, the type of effect it's going to produce. So we read kind of this top, we see training effects defined by changes that occur within the body due to a training stimulus. So we have multiple different effects that take place. So we'll classify them into different categories. So first is a partial effect. So this is produced, we see, by a single training means. Normally I would ask, what is an example of just a single training means? That's going to be after just doing one exercise. So like after bench press, what is the effect that was produced on the body just by doing one exercise? Acute effects, changes that occur following one exercise session. So let's say after a full upper body workout. So what changes took place acutely? Next is a cumulative effect. So these are continued training sessions over time. So we'll say after a few weeks of training, maybe a month or so of training, what changes have started to take place? Next is a delayed or a chronic effect. So we see these changes, they manifest over time. So this is like after an entire training program. So of even seasons of training, what effects have taken place on the body or what changes have occurred? And last is residual effect. So the residual effects, we see that word retention. So it means to retain something. So it's the retention of changes after we've stopped training. So that's cessation of a training program. So beyond the time period during which adaptations can take place. So these effects are important because we want to know how the body responds just to different stimuli. Successful resistance training programs know how to manage the adaptive and recovery responses of training stressors. They know how to handle accumulated fatigue and capitalize on the after effects of training stimuli. So what we're going to do on the next few slides is learn some different syndromes and theories that explain how the body adapts to stressful training. So we'll discuss 4 different constructs to understand how the body responds and adapts to stressors. The first is the general adaptation syndrome. So we see this was proposed in 1956 by Hans Seeley. He was a researcher of the biological effects of exposure to stressful stimuli. A stressor can be anything. It can be a physical, mental, or emotional stressor. But for the purposes of this class, we're going to discuss the stressor as a physical stressor, as in exercise. So there are 4 different phases, the first one being the alarm phase. So we see here the alarm phase occurs in the first few days to a week where the athlete has excessive soreness and temporary performance decrements. So with our alarm phase, I want you to think about the first time you started training ever or the first time you started training after a really long break. So what happens here? We have a disruption in homeostasis. The body experiences new or more intense stress due to your training. The initial response of the body is, first, we have an increase in hormones, like cortisol is our stress hormone. Also, our catecholamines, epinephrine, norepinephrine. And then over time, we're going to have accumulated fatigue, stiffness, reduced energy stores, possible dehydration, and then delayed onset muscle soreness. But after we kind of have time for our body to adapt, our body starts to adapt very quickly. And eventually, if we continue training, we're going to hit this resistance phase. What is this phase? Now the body is able to resist that exercise stress and performance returns to baseline. So here we're kind of back where we started. We're past that initial shock of our first training session or our new session of training. And now the body has started to adapt. We've adapted very quickly, and now we can resist that stress. So a body adapts to the stressor, returns to normal functioning. We have mobilization of energy stores. We've built up our structural capacity. We have an increased immune response, and recovery starts to take place. We have repair of damage and a return to homeostasis. The next phase is supercompensation. So this is when we reach a new level of performance capacity. So this is when we are now stronger, or we're faster, or we're larger. Whatever that adaptation is, we're now at a higher level of performance. So supercompensation only occurs if there is appropriately placed stimuli that can result in specific adjustments to the muscle that can further elevate performance. So what are some of those changes that occur with supercompensation? There's a mechanical change, which is change to connective tissue. We have increased connective tissue, increased strength, and increased stiffness. There's a chemical change, which is increased ATP and creatine phosphate stores. There's a metabolic change, which is increased glycogen and protein stores in the muscle. And then there's a structural change, which is increased contractile proteins and titin. So all those changes contribute to improvements in performance. The last phase is our exhaustion or overtraining phase. This phase can be avoided. It doesn't always have to occur. What is it caused by? Normally I would turn this over to y'all so you can answer everything that leads to exhaustion or overtraining. But what we know is if that stress persists and the body is unable to adapt to the stressor, that's going to present some of the same symptoms as the alarm phase. We have excessive loading, no rest, monotonous training. It could be an overly varied training program, poor nutrition, lack of sleep. All of those factors can cause this phase, but we know it can also be avoided. So here's what the general adaptation syndrome looks like when you plot it on a graph. So over here we have performance level, that's the purple line. And then we have each of these numbers which correlates with each of those phases. So I'll kind of go through this one more time. So we have introduction of a stressor. So we have a training stressor placed on the body, and you see this is our baseline performance right here. So baseline performance, let's say I make you do a workout that you've never done before, and that throws you into this alarm phase here. So now we're in the alarm phase. You read over here this box, initial phase of training, the body recognizes that stimulus, performance starts to decrease because we are fatigued, we're sore. And then you also see that 4, which is our overtraining phase, can bounce off of 1. So that's if the stimulus is too high, we don't have enough time, rest to recover. The stress, again, is too high for the body to handle. We can go into 4, or we can avoid that, and we go into our resistance phase. So now you see we are back to baseline performance. So our performance has resumed. We're kind of back, and we're on our way to an improvement or an increase in performance here. And then you see we can hit a new baseline level of performance. So now we're in the supercompensation phase. So new level of performance capacity that occurs in response to the adaptive response. So we've adapted, we are now better. And then what happens? We introduce another new training stressor. And now the phases happen all over again. But we're already at a new baseline. So we're not going to drop back down to where we started. We'll continue to increase over time. We see this right here. This is just intraday microcycle fluctuations in performance. So it's not going to be a linear line. We'll see some drops and dips in our performance over time. One thing to keep in mind is dimensions of each of these curves are highly variable to each individual, such as the slope, the magnitude, and the timing of each phase is unique to every single person. So another question I normally ask is, how can the overtraining phase be avoided? How can we avoid exhaustion? It's proper planning and management of those program design variables, such as intensity, frequency, technique training, and all of that. All right, so that's the general adaptation syndrome. Let's move on to the SFRAT. So what this is, we have stimulus fatigue recovery adaptation theory. This is an extension of the general adaptation syndrome, but this one's pretty easy to understand. So let's kind of first look at the definition. Training stimuli produces a general response, but that response is influenced by the magnitude of the stressor. Magnitude meaning how big, the total amount or greatness of the stressor. So here are kind of the steps. So the greater magnitude of the workload. So this just means a really hard workload. You did a really intense exercise. What happens? More accumulated fatigue. You're going to be more tired. You're going to be more sore. And then what does that result in? A longer delay before you can recover. Which means there's going to be a longer delay until the body can start to adapt. So basically our fatigue, recovery, and adaptation are all based on the magnitude of the work that we do. So the size of the workout, how intense the workout was. So a question right here. So what this question asks is basically what happens each time a new training stimulus is introduced. And when I say new, I'm meaning either something heavier, more intense, or a workout that you've never done before. What happens? The answer is this process keeps repeating itself. It's a basic pattern that persists if exposed to a stimulating load of greater intensity and volume than what the body is accustomed to. Next question is what happens if no new training stimuli is ever introduced? So if we use the same stimuli over time, what's going to happen? Eventually, or we'll start with, we can first maintain our level of performance. But then what happens? We go into something called involution. What is involution? It's the shrinking of muscle due to inactivity, atrophy of the muscle. So reduced overall capacity of training, so this is basically detraining, accompanied by the loss of neural factors, which decreases our strength, followed by a decrease in hypertrophy. What does this theory look like when plotted? So we have our performance level right here, and we're following this purple line. So our first is our training stimulus. So we have a training stimulus. We see up here our acute response. So immediately what happens with a workout? Fatigue. We're sore, we're tired. But then eventually we start to recover. And as we start to recover, we introduce another training stimulus. It may not be a new training stimulus, but it's still, we'll say, a workout. And then eventually we will finally recover and hit supercompensation, also referred to as overcompensation. And then this line here shows what happens if we stop training, what's going to occur. We're going to go into a detraining period where our performance and preparedness decreases, possibly putting us in a state of involution or muscle shrinking. So another question I ask students is, Why did we introduce? Why did we have a training stimulus here when we're trying to recover? So when we're sore and tired on our way back to our baseline, why did we train again? Answer is it's not always necessary to reach a state of complete recovery before we start a new training session. We've all trained and exercised when we're sore and we're tired. It's not fun, but we can do it. So we train around soreness and fatigue. We can use split routines. We can manipulate the workout intensity, make it lower, because if we wait until complete recovery, we may lose adaptations that we've already established, and we may start to regress due to a decreased training frequency. Because if we wait until we are 100% recovered to train again, that's going to take a few days, and that's going to be days of training that we could have achieved and built onto those adaptive responses. So yeah, that's kind of why we don't have to wait until we are completely recovered to do another workout. All right, here's our next one. So this is called supercompensation theory. So what this theory suggests is, and we can obviously read, the immediate training effect of a workout is the depletion of a certain biochemical substance. What is that biochemical substance? It's glycogen. And so we see down here in this picture, this is talking about glycogen supercompensation. But in order for our glycogen stores to increase above baseline, we have to deplete them. And that's what this statement says right here. So this statement here is talking about an athlete's preparedness. So an athlete's mentality towards a competition or training, how prepared they are, varies based on our fuel availability that we have in order to perform. So the amount of a biochemical substance available for immediate utilization. So the point of supercompensation is basically saying that we have to supply a restoration period, so a rest break or a day off, and that's what allows our glycogen stores to increase above baseline. And when they increase above baseline, that's called supercompensation because we have more fuel available for performance. This theory is based on the fact that the human body is an adjustable organism and will adjust itself to a higher level of fitness in anticipation of the future training sessions that we plan to perform. So fitness will surpass the initial level of performance capacity, but it's all based on our depletion of glycogen, our rest period to restore the glycogen, and then it increases above baseline so we can use it for exercise. So here's a picture, and if you look at this picture, it looks very similar to the SFRA theory. So what this says up here at the top, we see if the rest recovery intervals between sessions are too short, our preparedness decreases because the recovery period wasn't long enough for our glycogen levels to supercompensate. So if we look here, what is this figure even talking about? It's the time course of the restoration process, which contributes to the athlete's preparedness after a workout. So we see the vertical axis is both for the amount of the substance and for the level of preparedness. So we see depletion. So here's our workout. We work out, we deplete our glycogen. So our glycogen levels drop. But during our restoration period, if we give enough rest between workouts, our glycogen levels will increase, and they'll actually increase above baseline. So that increase above baseline is supercompensation. The weakness of this theory is in order for glycogen to increase above resting level, we have to be consuming adequate carbohydrates. So carb loading, proper training routine must be employed. ATP concentrations contribute to an improved performance but remain relatively stable even with vigorous exercise. We replenish ATP very quickly. This theory has lost decrease in popularity among scientists in recent years, but it does have validity for our aerobic athletes where glycogen is the main factor that determines performance. All right, last theory is our fitness fatigue paradigm. This one is more sophisticated than our supercompensation theory. But it still has to do with preparedness of our athlete. But it says preparedness is not stable, but varies with time. So this theory is based on the fact that immediately after we train, there are two after effects. So the two after effects of a workout are gains in physical fitness. We become more fit, but we also have an accumulation of physical fatigue. So we have the summation of two primary training after effects in response to a training stressor. This influences athletes' level of overall preparedness. So fitness gains after a few sessions are moderate in magnitude but long lasting, where fatigue effects are greater in magnitude but relatively short in duration. So after a single training session, an athlete's preparedness improves due to those fitness gains but deteriorates because we are so fatigued. But one thing to know is fatigue dissipates faster than fitness and allows for elevated preparedness if appropriate training strategies are used to retain the fitness while reducing the fatigue. It is assumed that for one training session with an average training load, the duration of the physical fitness gain and fatigue effect differ by a factor of 3. If the negative impact of fatigue lasts for 24 hours, the positive traces will remain for 72 hours. So this paradigm kind of shows this here. So we see every training bout creates both fitness and fatigue, summates to create a level of preparedness. The final outcome is determined by the summation of the positive and negative training effects. So we said that fitness and fatigue differ by a factor of 3, and fitness lasts longer than fatigue. Fatigue will dissipate very soon. So what this graph shows here is we have our training stimulus. It shows here that fitness is elevated, but we have so much fatigue due to that heavy workout that that's going to decrease our preparedness. So preparedness drops because fatigue is so high. Even though fitness is high as well, we're still not prepared. But in this box here, it shows preparedness is optimized as fatigue dissipates at a faster rate than fitness. So my question here is, how do we achieve optimal preparedness? So let's say we have a high training load. We're going to have elevated fitness, but also a high level of fatigue. If we do a low training load, we're going to have minimal fatigue, but we're also going to have minimal fitness. So both of those scenarios have a decreased level of preparedness. So I would usually turn it over to the class to see what answer we have. And the answer is sequencing our training loads and varying the workout in a systematic manner with use of high, moderate, and low loads. It's a balancing act of training. Each training factor stimulates its own degree of fitness, fatigue, and preparedness. So these are the residual effects of training. They serve as a fundamental concept underlying the use of sequential periodization methods. The after effects may carry over from one training phase to the next, and that's going to affect an athlete's overall preparedness. The time intervals between consecutive training sessions should be selected so that all the negative traces of the preceding session dissipate, but the positive physical fitness gains will persist. So the fitness fatigue paradigm is probably one of the most important factors in the periodization models. So normally I would turn it over to y'all and y'all would do a critical thinking where you would choose one of the models that you relate to the most and then you would share your experience. So instead of doing that, I just want you to think about which model relates or do you relate to the most and really kind of reflect on your experience with one.